So let's talk about what's a diffraction grating. So diffraction grating basically consists of an opaque piece of plastic or glass that normally light cannot pass through. So what we do is we cut lines into this plastic or glass that allows light to pass through. So we cut these lines inside here. How many lines do we usually have? In your lab, you typically may have between 100 lines per millimeter, way up to 1,200 lines per millimeter. That's how many lines you can have in 1 millimeter. So imagine now 1 mm, the distance is so small, and you're cutting in 1,200 lines. That means each of these lines must be very fine. Very, very, very fine lines. And what will happen? Example. Now, if you want to see how big the lines are, so let's try to imagine. So let's say this is in 1 mm. Not 1 mm now, okay. Let's say this is a zoom area of part of the diffraction grating. So let's say these are all your lines. I zoom in bigger so you can see. Now, if you have 1,200 lines per mm, then what is the gap between two lines? So wouldn't we be able to calculate this? So this is called your D, the gap between the lines. So this value is given as your N, number of lines per unit length. So what we will do is we take the D when we find the D by taking 1 over the N. That means 1 mm divided by the number of lines. That means in 1 mm you divide by 100 lines. That means each line how big? Correct? Or 1 mm you do 1,200 lines means one line how big? Correct? So that is your D. Okay? So you take the D. Now if you're using mm, so don't worry, don't have to change first. You take 1 over, let's say 1,200. So the D will end up to be in mm. So if you want to change in meter, after that only you times 10 to the power -3. So don't have to change at first. You keep whatever unit that you use. That means if this is per mm, then you don't mind, you just put 1 over 1,200. But you just remember, because it's per mm, your D will be in mm. But if your N is in per centimeter, then your D will be in centimeter. If the N here is per meter, then your D will be in meter. Alright? So after you get this, only you change at the end. So let's calculate this, what will you get? So what you will end up having, you will get like 8.33 times 10 to the power -7 meters. Now remember, the wavelength of visible light is between 4 to 7 times 10 to the power -7 meters, right? Okay, so in other words, can you see that your gap is just slightly bigger than your wavelength? That means it's comparable. So you get very big diffraction at each of the slit. So which means to say, okay, I'll show you the next slide. If I were to draw, zoom in how the slits look like. So now this is, imagine these are your slits. So I already zoom in even bigger. So at each of these slits, the light will spread a lot. Why? Maximum diffraction, because size of gap is almost equal to the wavelength. So at each of these slits, it will spread a lot. So what you will have is, you will have interference between all the light sources here. So imagine now our capital N is 1,200 lines per millimeter, and the size of your laser beam is 1 mm in diameter. Okay, let's say the size of the laser beam is 1 mm in diameter. So wouldn't it pass through 1,200 lines? So that means you have 1,200 light sources. So the light will come up from every one of these 1,200 light sources. So they will all overlap each other. So there will be interference between thousands of light sources. So therefore, you will also get constructive and destructive interference at certain positions. So when you get them, you will see a pattern like this. Okay, so let's say this is my diffraction grating. And let's say you're using red laser. So when it hits the screen at the back here, what will you see? So right in the middle, you're going to get a bright spot. That's where your laser came in. So let's make the laser a bit thicker. So this is where you're going to get the bright spot. So this one is called the 0 order, the middle. Then next to it, you will see another 2 bright spots. So this will be called the first order. And then next to it, you're going to get another 2 images, 2 bright spots, which are a bit further apart. So this will be called your second order. Okay, now wait, let me just shift. Okay, now then next to it, you will again get further away, and this will be your third order. So what is happening at these bright spots here? These are where constructive interference is occurring between all the light sources. So only in this direction, this direction, this direction, this direction are constructive interference happening between all the thousands of light sources. Now, which one is easier to achieve? Constructive interference between two light sources only, like the Young's double slit experiment, or constructive interference between thousands of light sources, which is easier to achieve? 2. Because for 2, you only need a path difference of lambda or 2 lambda or 3 lambda for the 2 waves. But now, you must have path difference of lambda, like for example, first order here, it is the path difference between each of the subsequent sources is all lambda, 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 lambda. Then you get the first order. Example, let's look at the next slide. So let's give an example how to get constructive interference. Now, imagine you are zooming in into the diffraction grating, and the light is all entering perpendicular to the grating. So the first assumption we are making is that the light enters perpendicular to your grating. So in order to produce a constructive interference, what must happen now? So let's take one particular direction, because what will happen is at each of these slits, it will actually spread. So they will all overlap in the middle here. So let's take one particular direction and let's talk about constructive interference in this direction. So you will notice that the wave from A will travel further than the wave from B, right? So there's a path difference here. Can you see this? So let's label this as your path difference. Okay. Now, the distance between one slit to the next slit, we already explained earlier on, that is your D. Now, and then the angle which they usually measure is from the straight through position. That means if this is the straight through position, this is the direction that we want, the angle must be measured from here to here. So that is called your theta. But if this is theta, okay, then you will notice that this is theta, right? Because actually I just took it from here. So the remaining inside angle here is 90 minus theta. So what will be the angle inside here? Okay, what will be the angle inside this one? It will be 180 minus 90 minus theta, because this is 90 minus theta, minus 90. Then you get this as theta. Okay? So then we use trigo. Trigo, sine theta is opposite over hypotenuse, right? Okay, so opposite over hypotenuse. So if I take opposite over hypotenuse, sorry, let me write down here. So sine theta is equals to path difference over D. Agree? So therefore, d sine theta equals to your path difference. For constructive interference, remember what must the path difference be? 1 lambda, 2 lambda, 3 lambda, and so forth. So isn't it n lambda? So therefore, d sine theta equals to n lambda. So that's how you get the formula for diffraction grating. So what it means is, if you want to get the first order constructive interference, the path difference between this ray and this ray will be 1 lambda. Then the path difference between this ray and this ray also 1 lambda. Then the path difference between this ray and the next ray also 1 lambda. Then you get the first order. But if you want the second order bright image, then the path difference between this and this must be 2 lambda. This and this also 2 lambda. This and this also 2 lambda. So each one of them must be the path difference. That's why it's so hard to achieve. Therefore, you will get fewer bright images compared to two source interference, because for them to all interfere constructively is a lower chance. Understand now? And that also explains why the spacings are not the same. Because when we look at the diffraction grating image, so remember what we drew just now, right? So you will notice that the spacing between the 0 and first order is different from the spacing between first and second, and then second to third. The angle, the spacing is getting bigger because your function is a sine function, sine theta. So how to use the formula? If you're using the formula d sine theta equals to n lambda, The D here refers to of course, the spacing between the slits lah, which is 1 over capital N. Now don't confuse with this N. This is small n, which is the order number. That means which one you want to solve. For example, let's say I want to solve for the second order, then the n I will substitute as 2. Now why is 2? Because remember, this represents the path difference. D sin theta equals the path difference. So second order is when the path difference is 2 lambda ma. That's why you substitute as n as 2. If you're solving for third order, then the path difference is 3 lambda ma. That's why you substitute as 3. So this represents the order number. But the theta must be measured from where? The theta must always be measured from the center. So if you're solving for second order, then you must use this theta. We call it theta 2. If you're solving for third order, then you must take this angle and we call it theta 3. And it is symmetrical on both sides, on this side as well. So the theta 2, which is here, if you take from here to here, the theta 2 must still be the same one. So it's also symmetrical one. Okay, that's how you use the formula. So if you're showing second order, using second order, so this is your second order angle theta 2, substitute as 2, then you can solve it. Alright, and the spacing will get further apart. Because why? There's a sine function here. So there's a theta sine theta there. So the spacing is not same. Okay, so for two source interference, the spacing is the same. But for diffraction grating, the spacing is not the same. Now, very important to remember, this formula is based on the assumption that the light must enter the grating perpendicularly. Why? Because remember when we were deriving the formula in the previous slide, we only took the path difference after the grating. That means you took in this direction or this direction, the path difference must be n lambda, right? But that is because when it comes in perpendicular means all the light will enter parallel. So is there any path difference between them before the grating? Don't have. But if it comes in at an angle, let's say like this, then there will be a path difference before as well. So if you got path difference before, then we cannot use this equation because this equation never considered the path difference before. So this formula, if they ask you what is the condition is that the light must enter perpendicular to the grating. Why? Because it assumes, this formula assumes that there's no path difference before the grating, only after the grating. Okay? Now there's another formula which we can use from here. Now, we can actually predict the number of orders you can see. Okay, so that means you can actually predict the number of bright images you can see. How do you predict? It's like this. We use back the formula d sin theta equals to n lambda. So therefore, your sin theta will be equals to n lambda over d. Agree? So what is the maximum value for sin theta? 1. So therefore, n lambda over d must also be less than 1. So your n must be smaller or equal than d over lambda. So this is the formula. You need to remember this. So if you substitute the value of d and the lambda, you calculate this value first. The n must be an integer smaller than this. Example, if let's say you get 4.7, then your n will be 4. You must round down, never round up. Then it's not 5. Okay? Now, once you get the highest order number, so what it means is your highest order is 4. So how many bright images and what is the highest order number is not the same. Highest order number is 4, but how many will you see on the screen? So remember, you will see the 0 order first. Then you got 1, 2, 3, 4. 1, 2, 3, 4. So total is how many?
8,
9, inclusive of the 0. So in order to get the total number of images, it will be 2 times the highest order number plus 1 for the 0 order. So be careful what they're asking you. Number of images will be 9. Number of orders is 4. Okay?